So class, welcome to the lecture number 12th of the course. So this being a very important lecture, so I am using my notes to teach. I have already prepared these notes and I will teach from these notes. So because I don't want to skip any of the important points, because there are lots of points, small points which are important. Okay, because now in this course, in this lecture, I will start with capacitor, and then I will teach inductors. Okay, and these inductor capacitors, they are very important for this AC analysis. Okay, because for AC circuits they can be solved. Means they often means have these equipments now, these elements, capacitor and inductors. Okay, in the circuit. So I already told you that we have three passive linear elements like R, L, and C: resistor, inductor, and capacitor. They are the passive linear circuit elements. Okay, out of these three elements, two are able to store energy storing, and one is energy dissipating. Okay, so this resistor, it only dissipates energy. Okay, so I am saying it is a energy dissipating element and it will not store any energy. Okay, however, inductor and capacitor L and C, they are the energy storing elements. Okay, so once the energy is stored in inductor and capacitor, that energy can be retrieved from these two elements. Okay, and that can be used anywhere in the circuit later. Okay, so first I will start with the capacitors. Okay, so what is the application of capacitors? The applications of capacitor means they find their application in means many fields, like in this now. If you will say these capacitors, they are used in electronic circuit. You must have seen your this inverter circuit at your homes. Okay, or this other electronic circuit, you must have seen capacitors, ceramic capacitor mostly, or electrolytic capacitor they are using there. And they are used in communication system. Okay, so in computer systems, computers, they are used as well as in the power system. So from a electronic means low power rating to a very high power rating. Okay, because these electronic circuits, they are a low power rating circuits. Okay, and these power systems, they are a very high power rating circuits. So I can say the capacitors are used in circuits ranging from low power rating to a very high power rating. Okay, so what is basically a capacitor? How a capacitor is created? Basically, a capacitor is created. It consists of a two metallic or conducting plate. This is one plate. This is another plate. This is the, I am drawing the front view here. Okay, so if you will look at the side view, it will look like this. These plates will look like this. Okay, so it consists of two metallic plates. Okay, and separated by some distance. Okay, and the distance is d, and this the space between these plates, it is filled with some dielectric medium. Okay, I'm saying the space between the capacitors, it is filled with some dielectric medium. Okay, so what are the dielectric mediums that can be filled? Dielectric mediums are that can fill this space. There, it is air. Air means there is nothing but air only. Okay, ceramics, mica, paper, etc. So these are the various dielectric mediums that can be used in a capacitor. Okay, so now this capacitor, what I am doing, I am connecting this circuit to a voltage source. Okay, means I am energizing this circuit, this capacitor. So the circuit will look like this. So if you will see, one plate is connected to the positive of the voltage source and the other plate is connected to the negative of the voltage source. Okay, so I'm saying when a voltage source is connected connected to the capacitor, a charge equal to plus q is deposited on one plate, and an equal charge but of opposite polarity means minus q is deposited on the another plate. Okay, so this is plus q, this is minus q. Where on which plate positive charge is accumulated? The plate which is connected to the positive of the voltage source, there positive charge accumulates, and a plate which is connected to the negative of the voltage source, there a negative charge is accumulated, but both the charges are equal. Okay, now the amount of charge that is stored on a plate, okay, the amount of charge that is stored on one plate, I am saying the amount of charge that is q, which is stored on one plate, it is proportional to what? It is proportional to the applied voltage v. Whatever voltage you are applying here, according to that, the charge will be accumulated here on a plate. Okay, so I can say that q is directly proportional to v. Got it? Q is directly proportional to V. So using the constant of proportionality, I can write Q is equal to C into V. Okay, where C is what? C is the constant of proportionality and is known as the capacitance of the capacitor. Capacitance of the capacitor. What do you mean by capacitor? Capacitor simply means capacity to store energy. Capacity to store energy. Okay, capacitor simply means capacity to store energy. So I am saying the capacitance of a capacitor, I am saying the charge accumulated on a plate is directly proportional to the applied voltage. So I can write Q is equal to CV, where C is the constant of proportionality and is known as the capacitance of the capacitor. So what are the units of C capacitance? The units for capacitance are farad, F-A-R-A-D, farad, which is denoted by the symbol capital F. Okay, so tell me, if I will, what will happen to the capacitance if I will increase the voltage? What will happen to the capacitance? Will capacitance increase or decrease? The capacitance will not change. If I will change the, once I have completed this circuit, so then if I will keep on changing the voltage, the capacitance will not change, but Q will change. Okay, C will remain constant. So C is not dependent upon the voltage that is applied on the circuit. Okay, C is dependent upon what? C is dependent of some other factors. What are the factors? C depends upon what is the area of the plate. Okay, what is the area of the plate? What is the distance between the two plates? And it depends upon which type of material is used in the space between these plates. Okay, C depends on these factors. So from here I can say what is C? C is equal to Q by V. So I can say C is equal to Q by V. So from here I can say that the ratio of charge, on one plate, I will denote it by Q, the ratio of charge on one plate to the voltage difference, V, okay, is called as the capacitance. Okay, I am saying the ratio of charge on one plate to the voltage difference V, because this voltage is the voltage that will appear across the plates. So I am saying the ratio of charge Q divided by the charge on one plate. Remember, it is a charge on one plate to the voltage difference between the plates is called as the capacitance. So I am saying ratio of charge Q on a plate to the voltage difference V is called the capacitance. Okay, so I am saying if I have a capacitance of 1 farad, so I will say it will be equal to 1 charge per volt, 1 charge, okay, 1 coulomb of charge per volt. Okay, because a unit of charge is coulomb. Okay, so it will be 1 farad will be equal to 1 coulomb per volt. Okay, now I was talking about the capacitance. This capacitance C किस पे depend करेगा? I told you C depends upon the distance between the plates, the surface area of each plate, and the permittivity of the medium between the plates. Okay, so the formula for C is epsilon A by D, where epsilon is nothing but the permittivity of the dielectric medium between the plates, area is the surface area of each plate, and D is the distance between the plates. Got it? Now, now I can say that C depends upon epsilon A by D. So what if I increase the distance between the plates? If the distance between the plates is increased, capacitance will decrease. However, if I increase the area of cross section of each plate, or surface, sorry, not area of cross section, but surface area of each plate, if I will increase, the capacitance will increase. Okay, and if I will use if I will fill the space between these parallel plates by some dielectric with high permittivity, so then at that time the capacitance will increase. Okay, now capacitance can be a fixed capacitor, it can be a variable capacitor. So what is the symbol for a fixed capacitor? I will show you here. So this is positive, this is negative, this is voltage V, positive, negative. If this terminal is positive, this is negative, so current will flow in this direction, I. Okay, so the capacitance of this capacitor I am saying C. So this type of capacitor is called as fixed capacitor. Okay, however, this is V. So I am saying this is plus minus, so current will flow in this direction. Okay, V, and I am saying this arrow. So because of this arrow signifies that we can change the capacitance of the capacitor. Okay, so this is called variable capacitor. Okay, now I told you the unit for capacitance is farad, F. Okay, so this farad is a very bigger unit. Very bigger unit means for 1 farad of this to make a capacitor of 1 farad, huge space is required. Okay, बहुत ज़्यादा स्पेस चाहिए. So what we do, instead of using bigger capacitor, this is a very bigger unit, so we take smaller unit. Okay, so that's why we say capacitance is usually taken in microfarad, picofarad. Okay, not even millifarad, in microfarad and picofarad. These are the smaller units of the capacitance. Okay, so next one important point I would like to add here. Okay, look, there are very small points which are very important. Okay, so I am saying if the voltage across the capacitor is greater than 0 and current is greater than 0, I will talk two cases. Number one, voltage greater than 0 and current greater than 0, or voltage less than 0 and current less than 0. Second case, if voltage into current is less than 0. Okay, so tell me, if voltage is greater than 0 and current is greater than 0, okay, means voltage is positive and current is positive. What will be the product of voltage and current? It will again positive. Okay, and if I am saying voltage is less than 0 and current is less than 0, what will be the product of voltage and current? Both are negative, so product will be positive, means power here will be positive, here will be positive. If the product V into I, it is positive, means V into I is greater than 0. In both the cases it is greater than 0. So I will say capacitor is charging. Then capacitor will charge. However, if I am saying if the product of V and I is less than 0 means negative, then I will say capacitor is discharging. Capacitor will discharge. So it is very important, means if you will say, okay, when voltage is less than 0 and current, why is it charging? Because we are concerned with the power, that is V into I. Okay, product of V into I, if they both are negative, their product will be positive. Okay, then it will charge. As long as V dot I is greater than 0, capacitor will charge. The moment V dot I becomes less than equal to 0, that means capacitor will discharge. What do you mean by discharge? By discharge, we mean that the capacitor is now supplying power, or we are or capacitor is now releasing energy. Charging means absorbing energy. Discharging means releasing energy. Charging means capacitor is absorbing. Capacitor is absorbing energy, and discharging means capacitor is releasing. Capacitor is releasing energy. Okay, so so let us now determine the VI characteristics of a capacitor. VI characteristics, well, what do you mean by VI or IV characteristics? Let us derive the current voltage relation of a capacitor. Okay, so we will use the basic equation. You know that current is nothing but rate of change of charge, dq by dt. You know that I is nothing but dq by dt. And what is q? Q is directly proportional to V here. Okay, so I can write q is equal to cv. From here I can substitute q here, so I can write d by dt of q is nothing but cv. So c is constant, I can write c dv by dt. C dv by dt. So I am writing that I is equal to C dv by dt. So the capacitances or capacitors which exhibit this relationship, they are called linear capacitors. So the capacitors which exhibits this relationship, they are called linear characteristics. And if I will draw the graph of current versus rate of change of voltage, okay, means I will take current on y-axis and I will take rate of change of voltage on x-axis dv by dt. So the graph between I and dv by dt, remember I am not taking the graph between I and v, I am taking the graph between I and dv by dt. So this graph will be a straight line. And what the slope of the graph or slope of the curve, what will be the slope of the curve? Slope of the curve will give us the value of the capacitance. So I am saying slope will give us the value of the capacitance C. So, okay, so most of the capacitors that are available, they are the linear capacitors. Okay, they are linear capacitors. So for a non-linear capacitor, this current voltage relationship, it is not a straight line. Okay, for a non-linear capacitor, it is not a straight line. Current voltage relationship is not a straight line. So if you will see here, you can see that I is equal to CV by C dV by dt. So that means that voltage across a capacitor, dV by dt, voltage across a capacitor, it is not changing instantaneously. Okay, it is not changing instantaneously, means I am saying that if I is equal to C dV by dt, so this dV by dt represents that voltage across capacitor does not change instantaneously. This means voltage across capacitor does not change instantaneously, means I am saying this type of waveform is not possible in a capacitor. Means if I'm saying this is voltage and this voltage is not changing with time, okay, it is constant, so there is no dV by dt. Okay, this is time axis, so not possible for a capacitor. Okay, on the other hand, if I have a waveform like this, है ना, so if I'm saying this is vt, v, this is t, this is v, this is t, so it is changing with respect to time, na. So this is this is possible. Okay, na. So this is not possible, this is possible. This type of circuit, this type of behavior is possible. Okay, so I was saying that this, I was saying that I is equal to C dV by dt. So let us integrate this equation. Okay, okay. So integrating both side of equation, suppose you can label this equation with anything, equation 1. So what will you get? If you will integrate, you will get Vt is equal to 1 by C integral from time minus infinity to infinity I t dt. Okay, so if you will break this limit into 2 is equal to 1 upon C integral from time t naught to infinity it dt plus 1 by C integral minus infinity to t naught it dt. So we are saying this, this is the voltage across the capacitor, okay, from time is equal to minus infinity to time t naught. Okay, and we are saying t naught is the time of interest. Time of interest means at this time either we are analyzing the circuit from time t naught, or we are saying that initially the switch is off. Okay, and we are turning on the switch of at time t is equal to t naught. Okay, so I'm saying suppose initially there was some current in the capacitor, because of that current, means from time is equal to minus infinity from the past history. Okay, I'm saying in the past there was some current in the capacitor from time minus infinity to t naught. So I can represent this term by v naught t. So it is, I'm saying Vt is equal to 1 by C integral t naught to infinity it dt, okay, plus Vt naught. Vt naught is nothing but it comes from this term. Okay, so where Vt naught, if I will say, I am saying initially this, why is this current in the circuit? Because we are saying initially there was some charge in the circuit. Okay, initially there was some charge in the circuit, because you know that Q is equal to CV. So because we are saying that initially there was some charge in the circuit at time Q t is equal to t naught, from minus infinity to t is equal to t naught. Because of that, the voltage in the circuit was Vt naught. Okay, so I am saying that this Vt naught is equal to Qt naught by C. This is the voltage, this Vt naught is the voltage across the capacitor at time t is equal to t naught. Voltage across the capacitor at time t is equal to t naught, and this Vt naught shows the voltage across the capacitor due to the past history of the capacitor current. Okay, this Vt naught is the voltage across the capacitor due to the past history of the capacitor current. So that is why we say that if the capacitor is initially charged, or if the capacitor is initially uncharged. If the capacitor is initially charged, so we will write it as Vt naught. We say that if the capacitor is initially uncharged, then this term will be equal to 0, because initially there was no charge, so Vt naught will be equal to 0. Okay, got it? So let us calculate power. You know that power is equal to V into I. So V into C dV by dt. So this is power. So what is energy or work done? Energy or work done, it is nothing but how much power is consumed from time t is equal to minus infinity to time t. So it is pt dt. So it will be C. I will take C because C is constant, minus infinity to t v dv by dt will cancel. So I am left with C minus infinity to infinity. Okay. Now here this limits will get no change, because initially it was the limits were based on time. Now the limits will change according to the voltage. So I will get C minus infinity to will be, it will what will I will replace the time here with the voltage which was at time t is equal to minus infinity with the, and here this upper limit I will replace with the voltage at time t v dv. Got it? So again I will have two components here. I will say I can replace it by C integral v at t naught, okay, to v at t v dv plus integral v at minus infinity to v at t naught v dv. Okay, suppose I am saying that initially the capacitor was uncharged. Initially the capacitor was uncharged means at time t is equal to minus infinity, the capacitor was uncharged. So this term will be equal to 0. So what I am left with? I am left with C. So v dv will be equal to 1 by 2 v square. Okay, from v t naught to v t. Okay, so I am saying initially it was uncharged, then from minus infinity to naught, so this term will become equal to 0. So I am left with this term. Okay, 1 by 2 cv square. So you know that q is equal to cv. So c into v you can write q or you can write v is equal to q by c. V equal to q by c. C multiplied by v is equal to q square by twice c square. So this c will cancel. So I can write w is equal to q square by 2c is equal to 1 by 2 cv square. So this is the energy that is stored in the capacitor. This is the energy stored in the capacitor. Stored in a capacitor. Energy stored in a capacitor. So this energy, this is called as the capacity of the capacitor. How much energy a capacitor can store, that is called as the capacity of the capacitor. So what are the properties of a capacitor? Again I am coming back to this my previous page. What are the properties of the capacitor? So properties, the first property is as it acts as an open circuit to DC. Why? It acts as an open circuit to DC. Why? The first property I am talking about, it acts as open circuit to DC. So if you will see DC, the DC is like this. This is time. I am saying this is voltage. Okay, so is there voltage change in the circuit? Is there any dV by dt? No, dV by dt, rate of change of voltage with respect to time, is 0. Okay, so we know that I is equal to, for a capacitor, I is equal to C dV by dt. So this is the DC waveform. Okay, DC voltage. So dV by dt in a DC is equal to 0. So what will be I? C multiplied by 0, it will be 0. So if a current is 0, what does that signifies? If a current is equal to 0, that signifies open circuit. So that is why we are writing here that it acts as open circuit to DC. Okay, second is voltage across the capacitor cannot change instantaneously, that we derived here from the current equation. I is equal to I dq by dt. From there we derived I is equal to C dV by dt. Okay, so from this point I can write that voltage across the capacitor cannot change instantaneously. Second property. Third property, ideal capacitor does not dissipate energy. Ideal capacitor is like, this is an ideal capacitor. Okay, there is no resistive part in this capacitor. Okay, only there is it has capacitance. So I will say that this capacitor, this is an ideal capacitor. There is no energy dissipating element. There is no resistor in the circuit, so this will not dissipate energy. This is because this is an ideal capacitor. However, we have non-ideal capacitors as well. So how non-ideal capacitors are represented? Non-ideal capacitors are represented like this. Means we have a resistance in parallel with the capacitor. Okay, so this represents the non-ideal capacitor. So a real, and this is a real capacitor. Okay, because there is nothing ideal in nature. Okay, everything that is available in the nature, it is associated with some non-idealities. Okay, so I am saying a real or non-ideal capacitor has a parallel leakage resistance. Okay, so and this leakage resistance may be of the order of, it can be of the order of 100 of mega ohms. Okay, it can be of the order of 100 of mega ohms. So if there is some resistive component in the circuit, so there definitely some it will dissipate some energy. And since I am saying this resistance is very high and it is connected in parallel, that is why the current flowing in this resistor, it will be very small. Okay, are you getting it? So next, okay, next let us solve this how resistances are connected in series and how they are connected in parallel. Means you have means we have discussed resistances in series and parallel. Similarly, fashion we will see capacitors in series and capacitors in parallel. So first I will talk about the capacitors that are connected in parallel. So I suppose I am saying that I have n capacitors which are connected in parallel. C1, C2, Cn. Here the current is I1. Here the current is I2. Here the current is In. Suppose I am saying the voltage here it is plus minus V. So same voltage is applied to all the capacitors because all the capacitors are connected in parallel. And here I have a current source, suppose I. Okay. So this, if you will apply KCL, Kirchhoff's current law at this node, I will be equal to what? I will be equal to I1 plus I2 plus In. Okay. So now I am saying instead of these n capacitors, I am representing the circuit by a single capacitor. The circuit diagram will look like this. This is C equivalent. This is V. This is I. Okay. This is same V. Okay. C equivalent. So I am saying this circuit is equivalent to this. So if in this circuit I is equivalent to what? I is equal to C equivalent dV by dt, this current. And what about these currents? I1 is equal to C1 dV by dt, I2 is C2 dV by dt plus Cn dV by dt. Okay, so now take dV by dt common on left hand side. C equivalent dV by dt is equal to dV by dt C1 plus C2 plus Cn. Okay, so dV by dt and dV by dt will cancel each other. So I will get C equivalent is equal to C1 plus C2 plus Cn. Okay, so what happens when the resistors are when the capacitors are connected in parallel, the equivalent capacitance is equal to the sum of all the capacitances that are connected in parallel. ओके तो इसका याद रखना, जो रेजिस्टेंस इन सीरीज में हो जाता है कैपेसिटर्स के साथ, वो पैरेलल में हो जाता है. ओके, so next let us discuss when the capacitors are connected in series. So again I am taking capacitors which are connected in series. For earlier I discussed about the capacitors which were connected in parallel. So this is my voltage V plus minus C1 C2 Cn, voltage here V1 V2 Vn. Okay, so what is V equal to? V1 plus V2 plus Vn. Okay, so here same current is flowing in the circuit I. Okay, so can you solve the circuit now? Okay, you know that I if I will replace the circuit by a single circuit, okay, so it will look like this: voltage source V, okay, so this is my C equivalent, this is I, same current. So in this case, this V will be equal to equivalent circuit. Uh, we know that I is equal to C dV by dt. So V will be equal to 1 by C integral I dt. So I will replace this V by 1 by C equivalent integral I dt. Now this current I, it is flowing in all the capacitors, so I can write 1 upon C1 integral I dt plus 1 upon C2 integral I dt plus 1 upon Cn integral I dt. Okay, so this I dt will cancel, and I am left with 1 upon C equivalent is equal to 1 by C1 plus 1 by C2 plus 1 by Cn. So look what happens. This this type of relation we are getting when resistors were connected in parallel. However, in case of capacitors, we are getting this type of relation when capacitors are connected in series. Okay, so I can say that equivalent capacitance of series connected capacitors is the reciprocal of the sum of the reciprocal of the individual capacitors. Okay, so if n is equal to 2, I am saying if n is equal to 2, so 1 by C equivalent will be equal to 1 by C1 plus 1 by C2. From here I can get C equivalent is equal to C1 C2 divided by C1 plus C2. Okay, got it? So what have we studied so far? We have studied that this capacitor, it acts as open circuit to DC. Voltage across the capacitor cannot change instantaneously. The capacity to store energy is given by 1 by 2 CV square. And we studied that in case of a parallel connected capacitors, the total capacitance is nothing but the sum of the individual capacitances of all the capacitors. And if the capacitors are connected in series, the equivalent capacitance of the series connected capacitor is the reciprocal of the sum of the reciprocals of the individual capacitors. Okay, so we also discussed about the linear resistors, non-linear resistors, ideal resistors or non-ideal resistors. Non-linear means non-ideal resistors. Okay, so next let us talk about the inductors. So for inductors, I am again shifting to my notes because this writing this theory it takes a lot of time, and then the duration of the this lecture it goes beyond 1 hour. So I want to keep it limited somewhere between 45 to 50. Okay, so inductors, like capacitors store energy, inductors also store energy. Okay, but inductors store energy in the magnetic field. Where? In the magnetic field. And what is inductor? I will show you. Inductor is nothing but consists of a coil of conducting wire with many turns. Okay, I am saying I have a coil. This is my conductor. Okay, what I am doing, I am making turns here. Okay, no, this wire has been converted into a coil. This is a conductor or wire. This wire, I have made turns of this wire and it has been converted into a coil. Okay, and this is called as inductor. Okay, so what I am saying, and consists of coil of conducting wire with many turns. Okay, now the voltage across the inductor, it is given by the relation V is equal to L di by dt. Okay, V is equal to L di by dt, or I can say that the voltage in an inductor across inductor voltage, I'm saying this is the voltage across inductor, this is the voltage across inductor plus minus V. So I can say that voltage across the inductor is directly proportional to the time rate of change of current. V is equal to L di by dt. Okay, voltage across an inductor is directly proportional to the time rate of change of current. V is equal to L di by dt. Got it? So the unit of L, okay, I can say that what I am saying, V is directly proportional to di by dt. Voltage across an inductor is directly proportional to the time rate of change of current. So I can use the constant of proportionality as the inductor L di by dt, because I'm talking about the coil. So the constant of proportionality here is inductor, and the unit of L is Henry. And the unit of L is Henry, and this L is called as the constant of proportionality, where L is the constant of proportionality, and this L is called as the inductance of the inductor. Okay, if you will see this inductor, it has the tendency to oppose the change in current. Okay, this inductor, it has a property that it opposes the change of current flowing through it. आपने 12th में पढ़ा होगा लेंजेस लॉ. ओके, cause effect opposes the cause. Okay, so I am saying the current that is flowing through the inductor, this inductor will try to oppose this change in current that is flowing through it. Okay, got it? So I am saying this is my inductor. Okay, it can take any shape, means inductor can take any shape. It can be like this. I have a wire like this. I can make inductor like this, or I can make inductor like this. Can be horizontal or it can be vertical. Okay, so the inductance of an inductor, it is given by formula. On which factors this inductance will depend? Means it is storing energy in magnetic field. Okay, so what is if you must have read permeability, mu is the permeability. I will teach you permeability in the coming lectures. What is permeability? Simply, it is the ability to get magnetized. If a material has high permeability, means it has more ability to get magnetized. So inductance, and this inductor stores energy in magnetic field. So obviously the material which has higher permeability, it will get magnetized easily, and it will store more energy in the magnetic field. So it will depend, number one, upon the permeability of the material, that is which type of material is there in the coil. Okay, so number one, it also depends upon the square of the number of turns of the coil. Okay, it also depends upon the area of the cross section of the coil, and inversely proportional to the length of the coil. Okay, so I'm saying the inductance of an inductor, okay, it is directly proportional to permeability, square of current, and area of cross section, and inversely proportional to the length of the coil. Okay, so inductor, I can have air core inductor, I can have iron core inductor. If I am using the iron core, what is the purpose of using the iron core? Purpose of using the iron core is to increase the permeability. Okay, if we are increasing the permeability, what is happening? If we are increasing the permeability, mu will increase, inductance will increase, and more energy will be stored. We will derive it later, what is the formula for energy. So I am saying I have different types of inductors. One, I am saying this is my positive terminal, negative V, the inductance is L, and the direction of current will be like this. This is air core, means the space between the turns. Okay, we have a coil and we have a hollow section in between. That hollow space, that is filled with air. The second type is iron core, L, current I. So here I am showing these two lines. These two lines represents the iron core. This is iron core type inductor, and the third I have here, inductor L, I. This is variable iron core. Variable iron core means we can take in and take out the iron core from the in the coil. Okay, so these are the three types of inductors that we have. Okay, so I have derived V is equal to L di by dt. Okay, from here I can say, if I will draw relationship, curve between voltage and rate of change of current, how the curve will look like, means I am on x-axis I am taking voltage, and on y-axis I am taking di by dt, rate of change of current. So the graph will be a straight line. Okay, and the slope of the graph will give me, the inductance of the, inductor L. Okay, So taking this equation, V is equal to L di by dt. Okay, so I can get di is equal to 1 by L into V dt. Now integrating both sides. If I will integrate both sides, I will get I is equal to 1 upon L, I is equal to 1 upon L, integral I is equal to 1 upon L, integral minus infinity to t Vt dt. Okay, so if I will break the limits from minus infinity to t naught, and from t naught to t I will get 1 upon L integral t naught to t Vt dt plus it naught. It naught is the current in the circuit before time t naught. Okay, from minus infinity to t naught means because of the past history of the inductor. Okay, so power in the inductor is given by V into I. So L di by dt is the V and into I. So energy is nothing but integral of the power. So again I will take the integral minus infinity to t. So it will be minus infinity to t. I will take L common, di by dt into I dt. Dt dt will cancel. So I am left with I dt in the I have to integrate I dt because this dt and dt will cancel. So I have to integrate I dt I di. No, we are taking the this na integrating current with respect to current. So the limits here will change. So instead of time, I will take current at time t is equal to minus infinity, and the upper limit will be replaced by the current at time t is equal to t. So if I will solve this. I will get E is equal to 1 by 2 Li square minus 1 by 2 Li square. But this current will be which current? Time when the time was minus infinity, means from the past. So if I am assuming that initially the inductor is uncharged, initially inductor uncharged means current in the inductor initially at time t is equal to minus infinity is 0. So I am left with E is equal to 1 by 2 Li square only. Okay. So let us see what are the properties of the inductor. What are the properties of the inductor? We say an inductor acts as a short circuit to DC. Okay. We say an inductor acts as a short circuit to DC. Why? Why short circuit? We are saying V is equal to L di by dt. So this is my DC current. I, this is time t. Is this current changing with respect to time? No. So what is di by dt here? Di by dt is 0. So V is equal to L di by dt. Okay, since di by dt is equal to 0, so V will be equal to 0. So what do you mean by zero voltage? Zero voltage means short circuit. Okay, if the voltage is 0, it represents short circuit. So that is why I am writing X as a short circuit to DC. Okay, again, an inductor, ideal inductor will not dissipate any energy. Okay, but because it has no resistive component. But I told you nothing is ideal. So a practical or non-ideal inductor, it will have some resistive component. Okay, and this resistance is called winding resistance. Why? I told you what is inductor. I told you what is it. It is simply a wire, conductor wire, and this wire is made in the form of a coil. Okay, so this is a conductor. Every conductor has some resistance. Every conductor has some resistance. So obviously this wire has some resistance. So that resistance is called winding resistance. Winding, W-I-N-D, winding resistance. Okay, so because of this winding resistance, there will be some energy dissipation in the inductor. Okay, so that is why we are saying that a practical or non-ideal inductor has resistance component. This resistance is called winding resistance, denoted by Rw. And this winding resistance is very small and this can be ignored. Okay, but this inductor, it also has some winding capacitance as well. Okay, winding capacitance due to the capacitive coupling between the conducting coils. Okay, Cw, winding capacitance is represented by Cw. Okay, I am saying this is because of the capacitive coupling between the conducting coils. So this Cw is very small and it can be ignored also. Okay, except at high frequencies, because you know that this capacitive reactance depends upon frequency as well. Okay, so the circuit for the non-ideal or practical inductor is shown like this. Inductor in series with the winding resistance, and this winding resistance is very small, and capacitance in is parallel with this circuit, and this capacitive winding capacitance, it is also very small. So I am saying the first, because of the first property where I am saying I is equal to inductor acts as a short circuit, means if we for a circuit like this, if I have a current IT, this type of signal is possible for an inductor. However, this type of signal is not possible. Okay, means it is allowed to apply this type of current now on the this type of current on this inductor, but not this type of current. Okay, next let us see what happens if the inductors are connected in when the inductors are connected in series and when the inductors are connected in parallel. Okay, so now first I will solve about the solve the circuit when the inductors are connected in parallel. So this is V plus minus Ln L2 L1 V1 V2 Vn I. Okay, so the total voltage V will be equal to V1 plus V2 plus Vn. So I can represent this V by V is equal to L equivalent di by dt, representing the whole inductor, all the inductors by some L equivalent. So I will get L equivalent, V is equal to L equivalent to di by dt is equal to V1 will be equal to L1 di by dt, V2 will be equal to L2 di by dt, and Vn will be equal to Ln di by dt. So taking di by dt common on right hand side and cancelling it with here with the di by dt on the left hand side, I will get L equivalent is equal to L1 plus L2 plus Ln. So in case of a series connected inductors, the net inductance or equivalent inductance is equal to the sum of all the inductors that are connected in series. So now you will solve the circuit when the inductors are connected in parallel. Okay, when the inductors are connected in parallel. So that is a homework to you. So it took me a lot of time, nearly about 47 minutes to complete this lecture, though for majority of the time I used my notes. Okay, refer to my notes. So if this whole was to be solved like this, it would have taken 1.5 hours. That's why I referred my notes in this lecture. So thank you very much for watching, and in case there is any problem, then we will discuss it in a interaction class which is scheduled on, I think, Thursday. Okay, thank you very much.